Hi everyone. No, we have a camera. Stand with, stand with. Yeah. Not even stand. Yeah, exactly.
So Jatin, you are not in the account.
Go to that. It's fine. You cannot go to that. How does it matter? Hi everyone, Syamantak Das is a faculty member at ICML Delhi. He got his PhD from IIT Delhi and then he spent 9 months as a visiting postdoc at MPI Germany and then another year as a postdoc at University of Bremen. His primary interests lie at the intersection of theoretical computer science and discrete optimization. In particular, he is currently interested in designing approximation and online algorithms for various kinds of combinatorial optimization problems, for example, scheduling or network design. Today, he will tell us about incremental metric bipartite matching. Take it away, Shyam.
Yeah, thanks, Jatish, and thanks Raghuvansh for the insight. And probably I should thank Nikhil for asking Raghuvansh to invite me. I don't know. But yeah, we make a lot of familiar faces, so it's really giving me authority to invite you. Okay. The talk is on matching and it's joint work with a bunch of people. So Ritesh is my PhD student at IIT Delhi and Minal is an undergrad, local boy, IIT Bombay. Sujay, some of you might be knowing, he's a faculty at IIT Bombay, and Sharat, who is like a collaborator since the last 2 years. So he's at NCSU right now. Okay, so just click on the slide. No. Just using the mouse. No. Here. Just click on the slide. Yeah. Okay. So the problem that, the problem on which this talk is going to be based is pretty much a classical problem. So here is the setting. Imagine that you have a bunch of red points, which we will call the requests from number one, and a bunch of blue points, which I will call servers from now on. And imagine that they are embedded in some metric space, right? So you could also visualize this as a bipartite graph, a complete bipartite graph between the red points and the blue points. The only sort of condition being that the distances, they should form a metric. Okay? Great. So, and what are we interested in? We are interested in determining perfect matching in this set of points. And assuming that the two sides are balanced, there will always be a perfect matching. And the fact that the graph is complete, there will always be a perfect matching. So what's the big deal then? Well, we want to find the perfect matching, which will minimize the total cost matching. Okay. So finding the maximum matching is sort of trivial in this case because it's a complete graph. You can even assign arbitrarily, but finding the minimum cost is what makes this problem interesting. So again, classical problem, in fact, the way it's posed in literature, it sort of shows up with various names. I think the most popular name is really weighted matching, right? Weighted bipartite matching. And in fact, I'm going to talk about one offline algorithm, which works even if you don't have the condition that this distance is form of metric. So I will point out specifically where in this talk the metric assumption is required. Okay. Now, what does incremental mean? Well, now assume that we are in a more dynamic framework where the blue points, that is the servers, they are known upfront, right? But the requests are getting revealed over time. Yeah. And at each point, I would like to maintain a partial matching on whatever requests have arrived so far. Okay. Now, I would like to point out one difference with this model and what is known as the online model of computation, right? Which is that in the online model of computation, it's kind of the same thing. You have to maintain a partial matching, but once a new request arrives, you cannot change decisions which you have made in the past. So you have to kind of, augment your solution. But here I am allowing you to do that. So you're allowed to change your past decisions, update your matching, but do it in a way so that at every point of time, you are comparable with the current optimal solution. Okay. So that's what I mean by incremental. The reason it's called incremental is because people use this to contrast it with the dynamic matching, which means that requests can also depart. So in this talk, I'm not going to assume that requests are departing. The servers are also fixed. Yeah. So maybe in the open problem slide, I will talk about those settings a little bit.
No, but what do you mean by what is over time? If you get a new request,
Yes.
are you also charged for move?
No.
We are not charged for movement. Yeah.
Okay.
So there are variants.
Then how is it different from each time instead
Yes.
of solving a
Yes, exactly.
completely
So-
new version of the problem?
Correct. So the thing is that I would like to update the solution much faster than doing it from scratch. So that's the challenge of the incremental setting. So every time a new request arrives, you are absolutely right. I can compute a matching from scratch.
Okay.
But the time that would require is as if you are solving the offline problem at every step. But what we would ideally like to do is not.
So it's a
spend so
dynamic,
much time.
it's a dynamic problem with no deletion.
Yes. Yes.
That's what, so you still have to work with amortized cost
Okay.
per.
Yes, I mean, one can talk about worst case cost too, but yeah, in this case, I will be talking about.
Okay.
Yeah, is it a question?
And so every time the number of requests is more equal to the number, so
That's right, that's right, yeah. So, I mean, here I will assume that the number of requests is sort of the same. And the number of servers is n, and the number of requests will start from 0 and it will build up to n. So the instance sort of ends there. Yeah, and while I talk about this, I'm inherently assuming that the value of n is known upfront, but well, in such settings, it's well known that you can get rid of these assumptions by what is known as a doubling trick, but I will not go into that.
But the servers are known, right?
The servers are
So you
known.
can get the value of n.
Well, that's the final n sort of. So the thing is, if an adversary stops your instance, let's say after n half requests, then you might be very mad. But here I'm assuming that n is really the correct n that you know, because the analysis kind of depends on that.
Okay.
Oh, the cost is the total cost of these edges. So these are the edges in the matching. So it's think of the assignment cost of every request to a server. The sum of that.
are they weighted pages?
Yes, and they form a metric. So think of it as a bipartite graph between the red point and the blue points. It's a complete bipartite graph, but the edge cost, they form a metric. So the other way to think about it is that these points are all embedded in a metric space. Yeah, but you cannot match a blue to a blue. You can only match a red to a blue. Yeah, because that's also another variant where you have a bunch of, let's say, points and let's say 2n points, and you just want to find a matching.
So one technical question. So I mean, when you say they're embedded in the metric space, it means that you have distances between the blue points and the red points also, right?
Yeah.
So if you just knew a complete bipartite graph and you knew the edges there, are these equivalent? Because then there are no triangles, right, in the complete bipartite graph. You have only
Well, there are no triangles, but if you think of a path between a red on this side and the blue on the other side, then the length of that path would be only larger than the cost of the direct connection. So the triangle inequality you can still define. Yeah, I mean, also because it's embedded in a metric space, distances are well defined between a blue and a blue point as well.
Absolutely, yes.
Just that the edges are not part of the solution. Yes, absolutely. More questions? Okay. So now before I go into the algorithm for incremental matching, let me take a quick detour and talk a bit about.
Wait one second.
Yes.
Is your goal to have the optimal at every point, or you try to get some approximation?
I will come to that in a bit. Yes, I will maintain an approximation, but yeah, I will motivate why that is. Well, not motivate really, but I will come to why that is. Yeah. So yeah, I mean, okay. So following up on Raghuvansh's question, the point is surprisingly, in fact, this problem is in polynomial time. So you can indeed find the mean cost perfect matching, even if you don't make the metric assumption. So even if you have arbitrary edge costs, you can find the minimum cost perfect matching using this classical method known as the Hungarian algorithm. Okay. So let me give you a sort of a bird's eye view of what this algorithm does. Okay. So it kind of works with the following linear program for this problem, and it's a very obvious assignment kind of linear program. So what is it saying? Well, it says that for every edge I have a variable XUV. In my mind, it's a Boolean variable, whether I take the edge or not. If I take, I pay for it. And then on each side, I impose these constraints that it's sort of the ZOR of the edges should be like one. Right? So you can take only one edge incident on every one. Yeah. So the constraints are separately imposed on every request and every subset.
By the way, minor nitpick. So
Yeah.
you say is that LP, but then you say XUV.
Yeah. So please excuse me. Okay. Now it's an LP. Yeah, Jerry. Okay. Good. He is always. Okay. Yeah. So technically, this is an ILP, but as always, we relax the ILP because solving ILPs are NP hard. In this case, it's not binary. I will come to that in a bit. So yeah, you can just relax this constraint and allow XUVs to take fractional values. It's quite clear that I don't need to impose the constraint XUV is at most one explicitly because it's implicit in the other constraints, right? Okay, so that's what is known as the LP relaxation, and and again, an amazing feature of this LP is that there is one vertex solution always, which is sort of integral. So if you solve this LP, then there is one optimal solution where which will actually give you the matching itself. Yeah. Great. But that's not what we are going to do because that takes too much time. Like solving an LP, yeah, theoretically it takes much more time. What we are going to do instead is take the dual of this linear program. Okay. So the Hungarian algorithm is essentially what is known as a primal dual algorithm. So we take the dual. And let us spend a bit on what the dual is telling us, right? So what the dual is really telling us that, okay, we have a variable for each vertex because the constraints on this side are on the vertices. And for every edge, what it's saying is that the total dual on the two endpoints, they should not exceed the cost of this edge. Okay. So interestingly, in matching literature, these duals are also known as prices. So I think the intuition is that, these are sort of monies that you are raising on the two sides to pay for the cost of this edge. And this will become a little more evident when I show you how we actually use the primal and the dual to design the algorithm. Okay. Okay. And yeah, one other important property of this dual is that we do not have any constraint on the YVs simply because we have equalities on this thing, right? So they are like free variables. In fact, some of them may take negative value in the course of the questions. All right. So yeah, just to make sure that all of us are on the same page. So let us take a small example. So imagine that these numbers are the YVs that I have put on the vertices, and the black ones are like the distances of the edge costs. Then as we can see that this is not a feasible dual solution. The reason being that this edge violates the dual condition, right? Because the dual it exceeds. The sum of the duals, it exceeds the distance or the cost of the edge. But there's an easy fix. I can just make it 0 and yeah. In fact, what is a trivial feasible dual here? Well, given that these are distances, they are always non-negative. So I can just put 0 everywhere and that's a feasible dual. So feasible dual is not hard to design. And in fact, okay, so why did we take the dual? Now, we are going to use the very well-known properties of primal dual pairs, which is that a feasible solution to the primal is always lower bounded by a feasible solution to the dual. And in fact, if we are able to produce such a condition that the feasible primal is equal to the feasible dual, then they imply that both are at their optimal. Okay? Yeah, that's the usual thing that we do in primal dual algorithms. But let's see how the Hungarian algorithm sort of builds on these ideas. Okay, so here is what you do. You start with an empty matching. Okay, so there is no edge in your solution so far. You have not matched any request to any server. And you start with the obvious feasible dual, which is YB equal to 0 every time. Yeah. So we start with a feasible dual, but we start with an infeasible primal solution in some sense. Okay. Good. Now, here is what we do at each step. At each step, I'm going to increase the size of my matching by exactly one edge. So I'm going to match one new request at every step. Okay. However, I'm also going to update my duals. Okay. Update my duals in a way which satisfies the following two conditions. Okay. So the first condition is the usual dual feasibility that we have already seen. So that should be still maintained for edges that are not part of the matching. Okay. However, once you add your edge to the matching, you better make sure that this constraint holds with an equality. So these are also known as tight constraints. Okay. The thing is, you add an edge to the matching, but before you add, you better make sure that the total dual on the two sides, they add up to the cost of the edge. Okay. And those of you who are familiar with this stuff would immediately recognize that this is exactly what is known as the primal complementary slackness condition. Okay. So from a bird's eye point of view, here is what the Hungarian algorithm does. It starts with a feasible dual and an infeasible primal. At every step, it iteratively builds towards a feasible primal solution. And at every step, it maintains the complementary slackness conditions. So this is the more non-trivial one. There is another complementary slackness condition, which is the dual one, that is sort of maintained trivially by this algorithm. Okay, so I'll not go into that. And at the end, you will end up with a perfect matching. And because you are able to maintain the complementary slackness conditions always, you will end up with an. Okay. So now the whole game boils down to how do you actually update your matching, right? Even in the offline settings. So you know the entire graph, of course, but how do you really make sure that when you add an edge, all these conditions are still satisfied? Okay. So one idea which is sort of crucial here, and that is crucial, I think, throughout the matching literature, is the idea of what is known as an augmenting path. Okay. So what is an augmenting path in this graph? So an augmenting path is always defined with respect to a partial matching, or any matching, not necessarily a partial matching. So let's say I have this partial matching. So these requests have been matched so far. And I sort of now, project the non-matching edges onto this picture. Okay. Now it turns out that for every free vertex on the left-hand side, which is not matched, you will always find a path to a free vertex on the right-hand side, given that the two sides are balanced. Yeah. That will alternate between edges which are in the matching and which are not in the matching. Okay. So such structures are very crucial in fact, flow literature in general, but in particular also matching.
It's a complete graph, right? So every path is measured.
That's right. Every path.
Is the direct edge.
Yeah, even a direct edge is a possible augmenting path. Okay. But I'm just showing you one of them because the choice of augmenting path is also crucial in this case. But yeah, in problems like finding the maximum matching, that's like that's okay. So yeah, might be only. Any questions? Okay. Good. Right. So yeah. So why does this path help us? Well, the thing is, if you are able to identify such a path, then I claim that I can increase the size of my matching. Right? What I would do simply is I would look at this path and I would flip the edges along this path. So whatever red will become black, and whatever is black will become red, right? But because it starts at a free vertex and ends at a free server, starts at a free request and ends at a free server, I will always match at least one more request. Okay. So if I'm able to identify an augmenting path, then at least I'm able to increase the size of my match. Okay. But the point is, I cannot blindly find an augmenting path. In fact, as Raghuvansh pointed out, because it's a complete graph, one augmenting path is trivial. You can always use the direct edge that exists between U and V, which I'm not showing here, but it does exist, right? The problem is we have to worry about costs now. And the way we handle costs is through this duality constraints that I showed you, right? So I have to be able to find an augmenting path so that I continue to maintain the dual invariants that are crucial to end up at an optimal matching. Okay. So in particular, even for this vertex, there could be two choices of augmenting paths. Like one is the one which I already showed you. So you go here, come here. But the other one is could be via this green, this green edge, right? So you go here, you come here, and you go to that free server. Right? So which one do we choose? Is the question. So let me again show you roughly through an example of how this works usually. Right? So suppose this is your picture right now. Again, the red edges are not part of the matching, and the black edges are part of the matching. Now here is what, so let's say you want to sort of find an augmenting path from this vertex to one of the free vertices, right? But you also want to maintain the dual constraint that whenever you add your edge to the matching, that edge should be tight, right? So the dual should add up to the cost of the edge. Now, how do you do that? Well, so right now from this guy, none of the edges are tight. So let's make one of them tight, by carefully adjusting the dual weights. And the obvious choice is you have a 3 here, you have a 2 here. So better raise the dual to 2 so that this edge becomes tight now. And the other edge does not violate the duality constraint because I cannot violate any dual constraint, right? So the obvious choice is the minimum of these two. Okay, good. The thing is that this edge was already part of the matching, which means that this was already tight, right? So what I'm trying to do is I'm trying to find an augmenting path on tight edges only. So that if I flip along that path, then the dual constraints, both the dual invariants will be satisfied. Okay? So from here till here, I am good, right? But now I'm sort of again stuck. The reason I'm stuck is because this edge is not tight, right? So what is again an obvious way to make it tight? Well, I can make this dual to be 2. But now I have a slight problem because the moment you make this dual 2, the dual feasibility is sort of violated for this edge, right? Because you have increased the dual too much, right? So the obvious fix is whenever you do such a thing, you keep on decreasing all the way up to the source. Okay. So I increased it by 1, I decreased this guy by 1, but I then increased this guy by 1 as well. Okay. So now I have an augmenting path on what I call the tight edges, and I can augment around that.
You chosen one for the purple vertex.
Sorry?
You would have chosen one for the purple vertex. The free vertex.
Good. So what you are asking is why didn't I raise the dual for the blue vertex, right? That is something the Hungarian algorithm does not do by design. Okay? There is no obvious reason why it doesn't do that, but it's a characteristic of the Hungarian algorithm that we always increase the duals on the requests and we always decrease the duals on the servers. Okay? Because the point is this picture is simple, but if you change the dual of servers, then it can affect other parts of your graphs which are not available. But if you do the opposite, then it's easier to update like this. Okay. Okay. So that's the sort of a bird's eye view. But in reality, how do you really how do you really implement this? Okay, and how do you implement this fast? So is there any way of, reusing some algorithm that we already know to find this augmenting path reasonably fast? Okay, the one with everything tight and all that, all satisfying all these properties, right? So here we use the notion of what is known as the reduced cost of an edge or the slack of an edge. Okay, what is the slack of an edge? Well, remember, this is the dual constraint that every edge has to satisfy. Now, some of them are already tight. We say that the slack is 0 for those edges. But for some of the edges, given that you have maintained this invariant so far, they will have a slack, right? So there is scope of adjusting the dual so that the edges become tight. Okay. So I define the slack on every edge. Okay. Like this. And what I do is the following. I find the augmenting path from a request to a server that minimizes the total reduced cost of the edges. Okay? And it's not hard to show that then you will end up with the same kind of path that I showed you by that step-by-step dual update procedure. It's a kind of a homework exercise, but it's not very hard. Okay? But now the question is, how do we find the path with the minimum total reduced cost? So here is an observation. The reduced costs are always non-negative. So I can just use the external algorithm. But remember, it's not on the actual edge costs, but rather on the reduced cost of the edges. Okay, so you can just use that. Right? So essentially, you can implement each step of the Hungarian algorithm by running extra. And then you have to do this n number of times because, your matching can only augment n number of times. Okay. So with this in mind, let us go back to the incremental setting. And now, we have at least one algorithm for the incremental setting, which is the obvious one, right? Which in fact, what we were doing in the offline setting as well, right? So what we do is when a request arrives, I just use Dijkstra to find an augmenting path, okay, on the reduced cost, which I have defined. And then, I have to update the matching and I update the dual weights in a certain way so that things are fine. Right? So what is the bottleneck now? Well, the bottleneck, there's not a bottleneck, and this is a correct algorithm, and this will in fact always maintain the optimal solution, right? Because you're always maintaining the complementary slackness conventions.
When a new request arrives, is it obvious that reduced cost will not be positive now?
Yes, that depends on this step, whether you are updating the matching and the reduced cost in a certain way. But you can pretty much use the same thing. So what you do is, okay, so here is the same. So you found, so you compute the path with the minimum reduced cost, right?
Yes.
And this is always from the new request.
Wait, it could be that you have a new request, the distance has just come in, but the distance is smaller than the dual variable you assigned to that server, right? Would that not it?
But the duals can go down then.
Will reduce to.
Yes. So this is why that's an advantage, that dual weights can go down. So the point is the dual weight of the new request will be exactly equal to the total reduced cost of this path, and the rest you can adjust accordingly. That's not very hard to do. Yeah, but as I said, it needs a proof that everything else remains fine. I mean, it's not an obvious thing at all. It's like a homework problem. Okay. All right. So that's one algorithm. But here is the thing, right? Remember, we are working with a metric space, right? So how much time will Dijkstra take for each update? It will take time, which is like n square. Right? O tilde of n square. Yeah, simply because there are n square many edges. Now, the question one can ask now is, can we have an algorithm that maintains a good matching, but it's sort of, okay, subquadratic in the number of vertices, but more importantly, is it sublinear in the sort of size of the graph? I mean, okay, here size of the graph really means n square. So can it be like sublinear in the number of edges? Okay. And surprisingly, nothing was known, even if, as Raghuvansh had asked, you allow approximation to your solution. So suppose I want to settle with an approximately optimal solution, some constant factor or whatever. Even then, this was not known. So that's where our what we have read of. So here is the result, and it yeah. So let me just unpack that. What is it saying? So the update time of our algorithm is n to the 1 plus delta, where again I'm hiding some logarithmic factors inside, and we have 1 over delta to the 0.63 approximation. Okay. So just to contrast, if you run Dijkstra, you would get O tilde of n squared, but here we are getting 1 plus delta. So delta could be any small. Okay. So that's the result. And remember, this only works for metric cases. We don't know anything about general weighted graphs, and we have no reason to believe that nothing is possible there. So that would be one of the interesting problems if some of you want to work on that. Okay, I lied a little bit when I said nothing was known. Something was known just before we submitted our paper. And so there was a paper last year by a bunch of people from Europe, like Goranci, some of you may, and then some other people. So, but their work was restricted to geometric spaces. So it's not only metric, but they assume that the points are embedded in the Euclidean R to the D. Actually, Euclidean is probably not required, although they don't explicitly say that in their paper. I don't think Euclidean is needed, but yeah, R to the D with D being a constant is definitely needed. Okay, and here they in fact have a stronger result than ours, right? Because the update time now is really sublinear in the number of vertices, not only the number of edges. So our result is n to the 1 plus delta, whereas theirs is n to the delta. Approximation ratio is kind of comparable. Right.
1 second.
Yeah.
So 1 plus delta approximation?
1 over delta.
1 over delta approximation. Okay.
N to the delta. Whereas ours is n to the 1 plus delta. Okay.
This is 1 minus 1 over 8.6.
That's what is it? Log 2 base 3?
Log 3.
Yeah. That's the source.
Is n to the delta is the worst case update time at any step or
Amortized. Amortized. It's not. However, okay, I did not mention it slide. I think there are some nice things about this as well. First of all, this worked for the fully dynamic setting also. So this will work even if servers and requests are departing. However, they need to make one assumption. I think that either they arrive in pairs or they depart in pairs. So you always have a perfectly balanced subgraph. That's kind of needed. Yeah, because their algorithm inherently depends on a notion known as disbalance. So that needs the graph to be balanced. Although I again believe it could be adapted, but they don't do that. Okay. So
this your
Yes.
your algorithm it's always n to the 1 plus delta update time.
This is
So
a
this is property of the analysis or no, the factor is at least always linear and not
yes.
no,
Yes. Say that again. Sorry.
No, your algorithm update time is always at least linear.
Are you asking about the lower bound?
Is the one needed
So
or-
is the one needed? That's a good question. So let me quickly think about it. Yes, I think even the very basic step of our algorithm will need like order like theta n. One of the like most important subroutines, it immediately loses theta n. So I don't think it's analysis.
So both of these algorithms are deterministic or?
Yes.
Okay.
No. Theirs is not deterministic. So let's put it this way. They use what is known as a quad tree. Okay. And what a quad tree does is, if you are in a geometric space, basically you do a hierarchical decomposition of your space. But then it's well known that if you do a deterministic decomposition, then you will suffer some distortion of points because you are now mapping each point to a point in this quad tree. So you cannot achieve this deterministically. You need to use what is known as a randomly shifted quad tree. So there is an inherent randomization there. But once you have that, the rest of it is completely determined. So that's the only source of randomness in their algorithm. But ours is completely deterministic. Yeah. But it's still amortized. So the runtime, like worst case, it could be as bad as this.
Is that why you said the constant because of pottery? Or?
Yes, absolutely. Absolutely. Yeah. So even if D is something like log n, it will not work. Yeah. Yeah, that's actually an open problem if one can do that. Okay. How much?
20 minutes.
Oh, okay. I can go until 5. Oh, okay, check. Okay, so let me tell you the idea of our algorithm. And in fact, let me tell you straight away that we kind of move away from the idea of finding augmenting paths. Although, as you will see that, the way we update our matching inherently uses the notion of augmentation, but I don't explicitly find an augmenting path. Okay, we do something different. And the inspiration is this classical paper by Gabo and Darjan, who gave an O tilde m square root n algorithm for finding mean cost perfect matching. Okay. By the way, this tilde actually hides not only a log n factor, but it hides something like a log delta, where capital delta, where delta I think is the largest edge weight or something like that. Yeah, it's the largest edge weight. Okay, so it actually depends on the values of the input, like this Gabo Darjan thing. Okay. But I guess that's pretty much the feature of most of the algorithm, except Hungarian, of course. Okay. So in contrast, Hungarian using Dijkstra as one Hungarian step would give you NQ. Right? So Gabo Darjan gives you 2.5. Okay, but what is the main idea behind, which suddenly led to this improvement? The idea is actually very simple. So assume for now that your distances are integers. Okay, and in fact, also assume that for some reason the optimal solution is like order of n, order of the number of vertices. Yeah, it's not hard to show that we can scale the distances in a certain way to make sure that these properties are true. Now, what they say is that, hey, look, the Hungarian algorithm imposes a strict dual constraint. Let us relax the dual constraint a little bit. Okay, let us say that I want my dual constraints to satisfy this, but with a +1. Okay, so in particular, for the edges which are not in the matching, I would allow their duals to go up all the way to distance +1. But whichever is part of my matching, I would still want them to be tight. Okay. Now it's of course not clear why this should not blow up the cost, because I'm not maintaining the complementary slackness anymore. Sorry, I'm maintaining the complementary slackness, but I'm not maintaining the dual feasibility of the original dual. But it happens. Okay. So I will not go into why. It's again not very difficult, but yeah, it needs some work. Yeah, it depends on how you are scaling things at all. Okay, so right, and one intuition about this +1 is the following, that because of this +1, if I have, let's say, two augmenting paths which are of similar reduced cost, but one has a much longer length compared to the other one. So length means number of edges. Then this +1 makes sure that you prefer the one which is sort of smaller in length, right? So if you think of, instead of running Dijkstra, if you think of a BFS-like procedure, then you will end up finding the path of shorter length if two of them have comparable reduced costs. So that's the intuition behind this +1. Okay. Right. So now let me show you a simpler version of our algorithm, which gives you a 1 to the 1.5 update time and gives you a 3 approximation. Okay. And at the end, I will tell you how to extend that sort of. Right. And the main idea stem from this paper by Pankaj Agarwal and Sharat, who is the co-author of this paper as well. So they achieve an analogous result in the offline setting. And again, this is only for metric spaces, right? So it's the exact analog of our result. It achieves the same approximation, and the total runtime is like n to the 2 plus delta, which means that amortized is like n to the 1 plus delta, if you divide by n. Okay. Great. So here is one of the things which we have to do. So assume that I know the value of the optimal solution. Okay, again, that's a big assumption, but those who are kind of familiar with online literature will immediately recognize that you can get rid of these things using what is known as a doubling trick. So if you are happy to lose another factor 2 or something in your approximation ratio, you can kind of break your sequence into phases depending on. So you start with a guess for the optimal, and then you have a way of tracking whether your guess is right or wrong. If your guess is wrong, you double the guess and so on and so forth. But here is one place where we are crucially using the incremental nature of our problem, because the value of the optimal solution only goes up. If it goes up and down, then this doubling trick is very hard to handle, right? Because the optimal solution can go down. And what if you have, guessed a very large value and now you are completely, it's problematic. Okay? That's one place. There are a few other places also. Okay, so what I do is, assuming that I know the value of the optimal solution, I use this sort of Gabor-Turgeon style scaling, which is I scale every distance by this quantity, which is epsilon opt divided by n. Okay, think of epsilon as a small constant. Right. So, well, and distances which are below sort of this threshold, I assume that I just ignore them, sort of make them zero. Yeah. I mean, I assume that the costs are zero for them. Yeah, it does not hurt me too much. So what are the consequences? So the first consequence is that the optimal solution is now n over epsilon. What do I mean by the optimal solution? Well, optimal solution under this scaled distances. Okay. The second important property is, if I am able to maintain a solution which satisfies this Gabor-Turgeon kind of dual feasibilities, then I can show that the weight of that matching or the cost of that matching is only a 1 plus epsilon factor away from the original object. Okay. And finally, as I said, now it's a little more well behaved because all the distances are integers, but interestingly, I can still prove that they form a metric space. Okay? In the sense that they satisfy triangle inequality. Okay, maybe saying a metric space is not, I don't know if it's technically correct, but what I really want is they should be non-negative and they should satisfy triangle inequality. So these properties are still, they still hold under this transformation. Okay, so assuming that we have such a graph, here is our algorithm. So let's say this new request has arrived, right? What I look at is what I call the admissible neighborhood of this request. What is an admissible neighborhood? Well, right now, of course, this is not part of the matching. So all the edges are not in the matching, in the neighborhood. But I look at only those edges which satisfy this condition with equality. Okay, so it's tight according to this dual feasibility condition. Okay. And what I do is extremely greedy. Okay. I just say that, hey, you get matched to just one of them arbitrarily. Okay. So I just match. So, but remember the property is that this is the admissible part of my graph. There might be other edges where there is a slack in this condition. Yeah. Assuming that I have maintained this condition so far.
So one question. So when a new request arrives, so you have to assign a dual variable.
That's correct. So right now I am assuming that let's say even So I wanted to avoid that. So let's assume that even without such thing, I somehow have these admissible edges. I will show you how to update, right? Yeah. So the thing is, let's just wait for 2 more slides. I think then, okay. That will answer your question. You're right. Because now the dual is 0. So there is no reason that this should be admissible. Yeah, so I have to raise my dual or something. But what I'm saying is inherently, I mean, you look at that admissible subgroup. Okay, good. But I have assigned it to S3, but okay. So when and this is very crucial. So remember now this becomes part of my matching. But if this becomes part of my matching, I have to now satisfy this condition. But remember, I had a +1 here. So I adjust that by doing a -1. Okay. And this is the most crucial step which will help us track the runtime of our algorithm. One of the most crucial steps. Okay. So whenever you do this kind of a greedy assignment, which is known as a push, you always decrease the dual of a server by 1. Okay. So you can charge the sort of pushes to decrement of the dual by a 1. That's the underlying thing. Okay. Okay, but now this definitely could have been matched, by match. I mean, some other request might have been matched to this guy. So now I have to do something. What I do is I simply repeat the procedure. Okay, so I look at the admissible subgraph. I again do the same thing. I decrease the dual of this guy by 1, and I keep doing this. Okay. Now suppose I am at a point where what Abhishek was saying happens, that there are a bunch of edges, but none of them are kind of admissible. And remember, I cannot do a push until I have an admissible edge. Right? So it's at this time where we do something known as a relabel operation. Okay? So the name is inspired from these push relabel style algorithms for finding a maximum flow. Right? So you push flow. If you cannot, then you change the labels of the vertices. Those of you who are aware of these algorithms. So this is exactly what we do. Okay. So now to answer your question, when this guy arrives, I mean, pretty much all the edges will be like this. So you start by adjusting the dual so that at least one edge becomes admissible. So you can imagine that this itself is the starting vertex.
Okay.
Right? So how does the algorithm look like? Basically, a new request arrives, you push, then some request becomes free, you try to push again. If you can push, then push. And remember, whenever you push, you are allowed to do a -1 because of the way things are set up. And when you cannot push, then you relabel, which means you update the duals. Okay. So that's the relabel kind of step. Okay. Now here is a problem that can happen, right? So suppose you pushed R to S3, right? And you knocked out R prime, right? And then you pushed R prime to S4, you knocked out R double prime. But what if now R double prime wants S3 again? Then you will end up pushing out R, right? So this kind of cyclic dependencies can happen. In contrast to if you had gone for an augmenting path where you will always end up finding a path, right? So if you just keep doing this greedy procedure, you might end up in cycles, right? So as such, it's not even clear whether this process will terminate, or even if it does, whether it terminates in terminates in reasonable time, right? In fact, let me give you another sort of worrying news, which is, think of what a push is really doing. It's looking at the admissible neighborhood of a vertex, and that search itself takes like theta n time, right? Because you have to find an edge which is admissible. So you have to potentially look at all the theta n neighborhood of this point. Yeah. So the only saving grace could be if somehow we are able to say that the number of pushes are not too high. Yeah, if the number of pushes are n at every update, then you will go back to this n square kind of runtime once again, right? That will not give you anything better than what Dijkstra was feeling. Okay. So here is where the dual weights come to our rescue. And so remember what we said is whenever we push, we have a decrement of 1 for some server. Okay. And now what we are able to show is that the total amount of change in server duals, and this is really an amortized analysis. Okay, this is one of the main lemmas that we prove in the paper, that if you look in an amortized sense across all arrivals, then the total change that happens in the server duals, that is upper bounded by the total dual change in the requests. Okay, and dual and requests start at 0, so it's only incrementing, and servers are only going down. Okay, the question still remains. Okay, what we have shown is that the total dual, okay, it's upper bounded by total dual of requests, but inherently duals are dependent on distances, isn't it? Because remember, I have to make the edges tight. Yeah. So how do you reconcile that? So here is idea number 2, really. I put a threshold on how long I will carry this process out. Okay. In particular, remember in this process, the request duals are always going up. Okay. The moment I find that the dual of some request becomes square root of n. Okay, so I start at 0. I'm incrementing everything by at least +1 because the edge weights are integers. The moment it hits square root of n, what I do is I will not try to match this request using this push level framework anymore. Okay, so I handle it differently. I promote it to some what we call level 2, and you will see why I call it level 1. Okay. So the overall picture is when a request arrives, I try to do the push reliable, but once I find in the process of push reliable, some request has reached a threshold of square root n, I just promote it to level 2 where I will do something else. Okay. The question is how many requests can get promoted, right? And the answer to that is only square root of n, and I will prove this in a bit. Okay, this is one of the nice cute proofs, but it can be done in one slide. Okay, so the number of vertices that go to the higher level, that is only square root n. Okay, but remember it's a balanced graph. If I have square root n free requests at level 2, then the number of free servers sort of which are not matched at level 1, that's also square root of n. And now I can just use Dijkstra on this subgraph, right? Because that will only give me kind of, right? It's square root n square, which is n. So at level 2, I'm great. The only thing I have to worry about is, am I good at level 1 or not? Okay, can I prove that the amortized runtime at level 1 is 1.5? Okay. However, before that, let me prove this property, right? That the total number of requests that reach to a dual of square root n or higher, that is only about square root of n. Okay, and might be missing some last times. So here is how you prove. So look at the picture at any point in time. Okay, and imagine that these two are requests that have reached this threshold. So they have reached the threshold of square root of n. Okay, now I'm going to use an operation which is again, it's strewn across matching literature, which is taking the symmetric difference with the optimal solution. Okay, and it's not hard to observe that if you take the symmetric difference between the optimal solution and the current matching, then you end up with vertex disjoint paths from each of the free requests, which looks like this. So they end up at a free server, okay, and they alternate between edges that are in the optimal matching and the edges that are in your current matching. Okay, and it simply follows from the fact that symmetric difference of two matching, so the degree of a vertex can be either 0 or 1 or 2. Right? It can't be anything else because both of them come from some matching. Right? But because these are free vertices in your matching, this can't be a cycle. Right? So it will end up at a free vertex. Okay. Now let us look at one such path. And assuming that I have maintained one feasibility, let us write these inequalities. Right? So I'm looking at this path. And for every edge that is in optimal, I know that I am one feasible, which means that I can write this constraint. And for every edge that is part of the matching, I can write the tight equality constraint. Okay? I add them up, except that I negate the terms which come from the matching. Okay. What do I have if I do that? Well, everything cancels out on the left hand side except the dual of the first vertex and the dual of the last vertex. Okay. And now, yes. So there are plus ones, which is why you have the 3 here. Okay. And then you have the distances. Okay, this is at most the edges from the optimal solution. Yeah, because the edges from the matching, they come with a minus sign, so I can kind of ignore because I'm putting a less than equal. Okay. Good. Now if I sum over all such parts, what do I get? Well, I get that the sum over the duals of the free requests.
Should be minus. It should be plus.
Which one?
Y bar plus YFS. The minus should be a plus, yeah.
Given
here. I mean, it's fine because that's what the dual should be.
Yes. Yeah. It should be a plus, but it's fine. Why? Because okay, good. So sorry. This should be a plus. Okay. But the thing is, this term vanishes simply because if it's a free server, then the dual is 0. Okay, and this is a very crucial property. If the dual was negative, then I could not have made these claims, right? But because it's a free server, it's not taken yet. All this term vanishes, and now I'm only left with this term. All of them add to opt plus n. But remember, I had shown that because of this scaling, optimal is sort of n over epsilon, right? So the entire right hand side is like a constant times n, and each of these terms is at least square root of n, which means you can only have square root n made such. That's the proof. Yeah. That's pretty much it. And now, basically what we show is that, there are square root n such, there are, yeah. Okay. So, and what happens at level? Okay. So that was the story of level 2, right? Because I only pushed like square root n vertices to level 2. What happens at level 1 is that, remember, each push can still take like theta n time because you're looking at the neighborhood, right? But what we can say is that in an amortized sense, the total number of pushes it's only square root of n, right? Because once if something goes to square root n, I don't do anything, right? I push it to the higher level. Yeah. And pushes are kind of upper bounded by the reliable step. So in an amortized sense, this is the number of pushes that happens at every step. I mean, think of this as like n squared times square root of n overall. Okay. Do I have time? I should wrap up. Yeah. Okay. So let me not go through the proof of why this is 3 approximate. Okay. Again, it uses the idea of okay. By the way, I won't go through the proof, but let me tell you one thing for sure, which is that this is the only place where I'm using the metric property of the edge costs. So far, whatever I have said, everything carries through, even if you have non-metric edge weights. But this is the point where I will inherently use the metric property. And the intuitive idea is that, so remember, I am sort of doing this 2-level algorithm. So things are pushed from level 1 to level 2. Now, imagine that in a real optimal solution, this request was matched to a server that was kind of taken away at level 1. And now this guy does not have access to this server anymore, right? It was taken away at level 1. Because at level 2, I'm just running an independent algorithm. And this could be potentially a problem because you are losing edges from the optimal solution, okay? But again, you can take the symmetric difference and use the metric property to show that, there still exists like an edge which is upper bounded by the optimal, the real optimal and the optimal at level 1. Okay, that's the rough idea. Okay, let me now really wrap up. So how do I get to whatever, the bound that I showed you? Well, the obvious idea, instead of using 2 levels, just use more levels. Okay. And these all stem out from back calculation, like how many levels you need. So you need roughly like log to the base 2 over delta levels. And yeah, there are some intricacies because 2 levels were sort of easier, you just push square root and vertices and continue. But now, since there are more levels, you have to be a little more careful about, what is the priority of assignment of request to servers and so on. But thankfully, everything works out. Okay, open problems. So first of all, I believe there is no reason that you should get a 1 plus delta approximation. You should. You can possibly. And why am I saying that? Because now, of course, we have this near linear time which can solve mean cost matching. Now we have such algorithms too, but those are more, I think, they use things like algebraic techniques, which I at least don't know how to, adapt to sort of the dynamic framework. But there are approximation algorithms offline which have this kind of bounds. So remember, our inspiration was Agarwal Sharat Kumar, which inherently have this 1 over delta to the 0.63. But now we have algorithms which give you an approximate flow, like 1 plus delta approximate flow in O tilde n to the 2 plus delta time. So those could be a line of attack. Can you kind of dynamize such algorithms? Okay.
Smaller the delta, you have to pay somewhere. No, here, everything is improving with delta.
Oh, I see. I think there would be a 1 over delta factor. Yes. Sorry. Yeah. There would be a. Yeah. Maybe as a log term, if I remember correctly. Like this times log of 1 over delta. Okay. And I think a slightly easier open question, honestly, because this might be hard, harder, let's say. But what if I now have like fully dynamic? So servers are coming, servers are also departing, or at least requests are departing. So inherently, I don't think this pushy level kind of, because the problem is that if a request departs, you suddenly lose a lot of dual. And remember this, increase of duals is a very crucial thing that we use in order to bound the number of push steps. So if you suddenly lose a lot of dual from your system, it may become a little tricky to, but there could be other.
You can just transfer the dual to somebody else or distribute the duals.
Wouldn't the method
Actually, that really makes sense because the way we prove it, it's not really like looking at one request and one server. You are right. I mean, it somehow says that, if I look at the neighborhood of a server, then the amortized change in its dual it's amortized across all the requests. So maybe that's a good point.
But the existing edges have to be tight, right? So once you distribute the
No, they don't have to be tight. They just have to be feasible. Only the matching edges have to be tight.
so the matching edges I'm talking about. So when you distribute the dual like
Well, that's not a reason to believe that it's not possible. I mean, could be.
Also, the issue of the opt decreasing.
That's, I think, one of the things I can never, I don't know how to handle. I think that could be a more glaring issue, that the opt is not monotonic anymore. So this assumption that I know optimal, that is very tricky to handle now. Because an adversary can always play this trick, right? So it will take your optimal solution to a very large value and then suddenly remove a bunch of things, which now takes your optimal down. So now what do you do now? All this. Monotonicity would be. Okay, I'm done. So thank you very much.
Question? I had this, I was thinking of this when you mentioned the level. So for 2, you have a level where you do the push tree level and another level where you do that extra. When you have more than 2, what happens in the middle?
Correct. So, great. So now I set my threshold instead of square root n, I set the threshold for dual values to be something like this, right? So at the ith level, it's like 3 to the I times delta. And I keep, so suppose now I start here with the scale metric. Now suppose a request reaches this threshold. So I push it up and I can prove an analogous theorem which says that the number of requests you push is roughly this much. But at this level now, I scale the metric differently because my n changes now, right? So it's a scaled version of the metric, but a different scaling, and I do the push to level A. How long do I do that? Till I reach like level mu, which is then you have very few vertices, so you can just run that. So it's a, that's why these values are like balancing out how many levels.
Your algorithm works for any metric.
For any metric.
So when vertex points, how is it you get to know all the n edges and the n distances? Is that how it is?
Yeah.
So that already is a n time. So do you get any? So you can't. That's why you have to have a n1 plus something.
That's true. That's true.
But suppose the metric is more nicer in some sense, like, in which you don't need to specify this.
Right.
Is there any way you can harness that?
Yes. So that's how exactly they do the geometric setting.
No, but the geometric.
Yeah.
Okay.
So the thing is that when you maintain this quad tree and a vertex arrives, what you do is you don't really look at all distances. What you do is, because it's on a geometric space and there are data structures which give you the nearest neighbor very fast, and you can sort of use those kind of algorithms to kind of map it to the cell in your structure. Yeah, it should work. Yeah, exactly. Although they just say that it's Euclidean, I think it works for any LP. Maybe the P will show up as some factor somewhere, but other than that,
What about if we will say some shortest path metric, but I tell you it's from bounded degree graph.
Yeah.
Therefore, you don't have to reveal.
So, okay, so here is what
the underlying metric is the shortest path metric, but the graph is only a bounded degree.
Yes. So
I reveal only d pieces of information.
So if you allow me like a polylog approximation, then I think I possibly know how to do this.
Okay.
And the reason is because you can embed shortest path metric, you can even embed any metric on these what are known as hierarchically separated trees with a distortion of log n.
Okay.
Right? But that's offline. However, I think there are papers by this group, in fact, Goranci and all, who can also do this dynamically. So you can maintain these hierarchically separated trees in a dynamic sense. Okay. And now when a new request arrives, I think you have a way of knowing directly like which leaf of this tree it is. So if you're allowed like polylog loss, okay, but I think the update then is like polylog n. You don't even need like into the epsilon or anything if you can maintain an HST. Okay. Yeah, but quad trees are a sort of different version of HST, which is why. That's fine. All yours. So now, should I press escape? No.